So, good morning, all the participants. Uh, Today, we are on the last day of this GAN course on automotive emissions control and scopes of alternative green fuels. In the first session, starting at 9 a.m., we are having our lecture number 2 from our Professor Sivalingan Murugan from the Department of Mechanical Engineering, NIT Meghalaya, NIT Rourkela. He will talk on washed heat recovery options in fuel cells. So I welcome Professor Murugan sir for this lecture and over to you, sir.
Thank you. Thank you very much, Professor Biplab. Good morning, all the participants. Today, my lecture is waste heat recovery options in fuel cells. Yesterday, I talked about the different alternative fuels uh, which can be used, which are used and can be used in automotive vehicles. The examples include biodiesel, of course, natural gas, LPG, hydrogen, ethanol, all these things I told. There are, of course, liquid and gaseous fuels. In addition to that, of course, we have electric vehicle, electric battery operated electric vehicles, and fuel cell operated vehicles. Fuel cells, of course, can be combined with electric vehicle mode, so that we can call it as a hybrid vehicle. Now, I will talk about fuel cell basics and then what are the waste heat recovery options from fuel cells. As you know that internal combustion engine in which fuel and air are supplied, they are burnt inside the engine. The heat which is generated or produced by burning the fuel air mixture is converted into mechanical work. And then, of course, according to the requirement, the mechanical power can be directly used to propel vehicles, or the mechanical work can be electrical energy with the help of generator. As in automotive vehicles, we need only mechanical power, so the IC engine can be directly coupled to the wheels of the vehicles. Now, the slight difference between fuel cell and the IC engine is that how the energy is converted from the fuel to electrical energy. In fuel cell, the chemical energy possessed by a fuel is converted into electricity by electrochemical reaction. So there is no combustion taking place inside the engine. Rather, the fuel and air, they are supplied to a fuel cell and electrochemical reaction takes place. As a result, we get electrical power output. So here the fuel cell is a device where you will admit fuel, you will admit, you will supply fuel, you will supply air in two different electrodes, and the electrochemical reaction that will take place between the electrodes. So here you can see in a fuel cell we have a cathode, we have an anode, in between them we have electrolyte. So fuel is fed on the cathode side, and the the air or oxygen that is supplied on the anode side. So here you can see an illustration of your fuel cell, picture of your fuel cell that's shown on the slide, top side, top right side. That's a schematic diagram of a fuel cell. So here you can see left hand side fuel is supplied. So there you have you know uh, you have anode I'm sorry, actually I told fuel is supplied on anode side, air is supplied on cathode side. If I do mistake, I apologize for that. Fuel is supplied on the anode side and the air is supplied on the cathode side. So when fuel, it passes through the electrolyte and the air passes through the electrolyte from the cathode side, an electrochemical reaction it takes place. As a result, if you connect an electrical circuit, you will get electrical power output. Now, we don't require any combustion action at all. Straight away feed the fuel, feed the air, and you will get electrical power output. But we have two products during this electrochemical reaction that are obtained. One is water with the heat, and of course second is electricity. That is, the electricity is a main product, whereas water is also obtained. But due to electrochemical reaction, there is some heat generated that will come along with water. Next slide, please. Now, we have studied the different power sources or energy conversion devices in our early studies. It may be BTech, undergraduate or postgraduate. Here I am showing a comparison of different stationary power sources like heat engine. In heat engine, we have internal combustion engine and external combustion engine. Then we have electrical battery. Then we have fuel cell. I am comparing the fuel cell parameters or some of the important descriptions with the heat engine and electrical battery. Now, if you see here, the fuel, what type of fuel we use in heat engines, we use hydrocarbon. It can be, petroleum fuels like petrol, diesel, or alternative fuels like ethanol, natural gas, LPG, natural gas, whatever it may be. They are all hydrocarbon fuels. In addition to that, of course, we use hydrogen. In the electrical battery, we don't use any fuel at all. We simply charge the battery by giving electrical input and we discharge electrical output. In fuel cell, we need to supply fuel. Generally, of course, hydrogen is used as a fuel. But of course, with the reforming actions, we can also use any hydrocarbon fuel. For example, you can use biogas that can be reformed and that can be used as a fuel in fuel cell. Then oxidizer. Oxidizer means oxidant. Since oxygen is available in air, you can directly use air as an oxidant in heat engine. Of course, pure oxygen is costly. To produce oxygen, extract oxygen from air is costly. Therefore, we can directly use air as an oxidant in heat engine. In electrochemical battery, we don't require oxidant or oxidizer at all. But in fuel cell, we require air or oxygen. Generally, as again, air can be supplied directly. Then the nature of energy release. Generally, of course, we get heat during combustion in heat engine, whereas in electrical battery, due to electrochemical reaction, energy is released from the discharge. Electrical energy is discharged from the electrical battery. In fuel cell, of course, as I told, because of electrochemical reaction, the energy possessed by a fuel is converted into electrical energy as a result of electrochemical reaction. Then what kind of products we get in heat engines, as you know, whether it's internal combustion engine or external combustion engine, we get heat energy. Then, of course, we get different pollutants like carbon dioxide, carbon monoxide, unburnt hydrocarbon, particulate matter, oxides of nitrogen, etc. In electrical battery, there is no harmful pollutants. We get product electricity. In fuel cell, we get mainly electricity and water is also obtained. Of course, in heat engines, when combustion occurs, you get two main products: CO2 and water. If the reaction is completely, if the combustion is complete, so you'll get, of course, carbon dioxide and water as products, and then heat energy you'll get. But depending on the supply of air, of course, we may get carbon monoxide, unburnt hydrocarbon, and CO2. In addition to that, you will get oxides of nitrogen, particulate matter, depending on the quality of fuel. Then thermal efficiency. As you know, heat engines have a maximum thermal efficiency of 40. Of course, nowadays we can have 45% with advanced engine technologies. Electrical battery, of course, they are capable of delivering electrical energy from electrical battery up to 90% efficiency. And the fuel cell, we can have the efficiency, conversion efficiency up to 70%. Then pollutant, as I told, different pollutants are formed in internal combustion engines due to the combustion of variety of fuels what you use. So as I told earlier, CO2 you will get, and water vapor you will get in the form of product when the combustion is complete. If the combustion is incomplete, you will get COHC, like that. In addition to that, of course, you have oxides of nitrogen, oxides of sulfur, particulate, etc. In electrical battery, there is no pollutant. Of course, there is a negligible pollutant arise from an electrical battery. In fuel cell also, there is a negligible pollutant arises from the fuel cell. Then startup, of course, as you know, internal combustion engines are a bit difficult to start. You have to crank the engine. But in electrical battery, you can discharge electrical energy. You can tap electrical energy. So you can easily start. In fuel cell also, you can easily start the fuel cell. Because there is no, crank mechanism and all to start the engine. There is no piston cylinder arrangement in a reciprocating engine like petrol engine and diesel engine. Here, simply you are supplying fuel and air, you get electrical energy. That is one of the best advantages, what you say, in fuel cell. Then part load operation. In part load operation, heat engines, of course, they exhibit very good performance. Electrical battery also, they exhibit very good performance. Similar to these two, fuel cell also, they show very good performance. Next, please. So as I told, of course, this top figure, it illustrates how the energy conversion is obtained in a load. So fuel is supplied on the anode side, oxygen is supplied on the cathode side. If you connect anode and cathode with an electrical circuit, normally we get electrical load, and you have to have electrolyte in between anode and cathode. So water is also obtained, as I told. So here, of course, the bottom figure, it shows if you want to use, of course, any hydrocarbon fuel. Nowadays, people are working on to use biogas, methanol, in fact, other fuels. So in that case, they need a reformer or fuel processor. With the help of your fuel processor, first you reform the fuel, which will have more purity to supply into the fuel cell. Otherwise, as on today, hydrogen is the best fuel to be used in a fuel cell. That's why yesterday I told there is a large requirement for hydrogen uh, in order to use it in automotive vehicle operations, particularly if you use internal combustion engine, hydrogen engines. If you want to use hydrogen engines, then you need hydrogen. Same way, if you want to operate a fuel cell in automotive vehicles, then there also you need hydrogen. Therefore, a large quantity of hydrogen is required in both applications. So this is what you require now. Of course, here you have a fuel cell that can be, connected. Many fuel cells can be connected, and that can produce the required amount of power from the fuel cell stack, and that power can be utilized to operate an automotive vehicle. Next, please. So here, of course, the electrolyte substance that usually defines the type of fuel cell that can be made from number of substances like potassium hydroxide, salt, carbonate, phosphoric acid, like that. So as I told, the most common fuel used as on today is hydrogen. In fact, if you see the anode and cathode materials are very, very important to get the maximum electrical energy conversion. So if you see, uh, normally a fuel cell that produces a voltage from 0.6 to 0.7 volt at full rated load, of course, depending on different parameters of a fuel cell, you can get maximum conversion efficiency. So many parameters that I will not talk about that, like activation loss, ohmic loss, mass transport loss, all are there. Because of them, voltage decreases as current increases. Next, please. Now, fuel cell is a device that converts chemical energy into electrical energy. That is the basic concept. But fuel cell can be classified mainly by three ways. One is based on temperature, second one is type of electrolyte what you use, and the third one is according to the nature of fuel or type of fuel you use. Based on the temperature, fuel cells can be classified as low temperature fuel cell, medium temperature fuel cell, and high temperature fuel cell. And type of, according to the type of electrolyte you use, it may be aqueous or non-aqueous, and molten or solid electrolyte fuel cell. According to the fuels we use, it can be hydrogen supplied fuel cell or fossil fuel based or hydrocarbon based fuel cell. And of course, alcohol fuel cells are also there. Then some people they use hydrogen as a fuel. In addition to all these things, nowadays there is a separate fuel cell called microbial fuel cell is also emerging. Next. So the type of fuel cells can be given in different names according to the, of course, as I told, the classification on the last slide. So here we use acronyms for different fuel cells what we use. Like alkaline fuel cell is designated as AFC. Then direct methanol fuel cell is called DMFC. Phosphoric acid fuel cell is called PAFC. Proton exchange membrane fuel cell is known as PMFC. Then solid oxide fuel cell is called SOFC, and the molten carbonate fuel cell is known as MCFC. Why I tell all these acronyms? Because hereafter I'll always talk like AFC, PFC, PMC, PMFC, like that. So you'll have to quickly understand the terms. That's why I showed this acronym. Next, please. So here, of course, the illustration gives the temperature, operating temperature of different fuel cells. As I told, fuel is supplied on the anode side, air is supplied on the cathode side, and in between that you have electrolyte. Now, proton exchange membrane that can be operated between 50 to between 50 and 150 degrees Celsius. Phosphoric acid fuel cell, it can be operated up to 200 degrees Celsius. Molten carbonate fuel cell, it has an maximum operating temperature of 650 degrees Celsius. Solid oxide fuel cell, they can be fuel cells. They can be operated between 700 to 1000 degrees Celsius. So here you can see solid oxide fuel cell, SOFC, is having a very high operating temperature, 1000 degrees Celsius. You can operate up to 1000 degree Celsius. Therefore, solid oxide fuel cells can be used as stationary power sources where you can produce large amount of power. But commonly, the proton exchange membrane fuel cells, which are known to be low temperature, low operating temperature fuel cells, they are used in automotive vehicle applications. Next, please. So here, of course, so what kind of fuels we can use and for what application is shown in this slide. You can see normally hydrogen that can be used in PMFC and AFC, alkaline fuel cell. Then, of course, methanol and ethanol, they can be used in DMFC, direct methanol fuel cell. Then, of course, you have variety of fuels like biogas, biomass, natural gas, gasoline, coal, all can be used as fuels in fuel cells like SOFC, MCFC, PMFC, and PFC. But the thing is that if you want to use these fuels, you need to have a reformer before you supply the fuel into the PMFC or PAFC. And of course, the bottom of the chart, it shows the applications of fuel cells in different sectors. So we have different sectors like portable, transport, road, maritime, air, and stationary applications like residential and industry. So fuel cells can be used in all the sectors. Like nowadays we have diesel generator. How we use diesel generator, same like that, to produce power. To produce power as for standby application, we can use fuel cells. For example, if we take a data center, there if you want to provide a stationary power source, then instead of using a diesel generator, you can use a fuel cell. So more in developed countries, of course, data centers are integrated with fuel cell power backups. Next, please. Next, please. So here again you can see the application of fuel cell in different power output capacities. You can see the fuel cell can be used or applied from the lowest capacity, like a cell phone, up to the power generation in megawatts. So here you can see fuel cell can be used in cell phone, computer or laptop, military battery, home electricity, automobile, hospitals, or commercial complexes, then submarines, power plant grids, means they can be directly producing power and that can be supplied. So if you just see, the fuel cell power can be obtained from 10 10 watts to maximum of 10 power 7 watts. That means you will get megawatts. Up to megawatts you can produce power from fuel cell. Next, please. So again, the same type of slide is shown, but with different capacity and different fuel cells what we can use. Say from 1 watt to 100 watts, you can use DMFC, direct methanol fuel cell. PMFC you can use for a power range from 10 watts to 100 kilowatts, and SOFC you can use it from 1 kilowatt to 100 megawatts, because its operating temperature is very high. Therefore, you can use it to produce power up to 100 megawatts. And alkaline fuel cell, you can use it from power ranging from 100 watts to 100 kilowatts. And lastly, molten carbonate fuel cell, MCFC, that can be used for power ranging from 100 kilowatts to 100 megawatts. Next, please. So here I would like to show some comparisons between the fuel cells what we have. Here the left hand side it shows the fuel cell what we use, like PMFC, alkaline fuel cell, AFC, PFC, phosphoric acid fuel cell. So in this slide, these three types are shown. The second column, it shows the operating temperature. Third column, it shows electrolyte, then stack power output, then efficiency, application, merits and all. So here, as I told in the previous two slides, the operating temperature of PMFC, it is in the range of 50 to 100 degrees Celsius. So the type of electrolyte what we use, that is perfluorosulfonic acid, and the power output, as I told in the previous slide, you can use up to 100 kilowatts. Efficiency, operating efficiency is about 53 to 58% in transportation, when you use it in transportation. And when you use it in a stationary application, you can get 25 to 35%. And when you combine with the heat, when you use it in combined heat and power source, then you can get the maximum efficiency of 90%. And of course, different applications of PMFC is there. You can use it as a backup and a portable power. You can also use it for distributed power generation, and of course, very low power output generation. Then, of course, you can use it in transportation sector and specialty vehicles. So the merits are solid electrolyte that reduces corrosion and electrolyte management problems are reduced, and you can have low operating temperature, and you can quickly start the fuel cell. Alkaline and AFC, next one is, of course, temperature range I told in the previous slide itself. What kind of electrolyte is used here? It's aqueous solution of potassium hydroxide soaked in a matrix. And the stack power output is shown, already I told in the previous slide. Conversion efficiency is about 60%, and when you use it with low grade heat, then you can get up to 80%. And you can use it for military purpose, military vehicles. And here the advantage is that cathode reaction is faster in alkaline electrolyte, that leads to higher performance. And you can use it for use variety of electrolytes. Then next, PFC, of course, you can produce power up to 1 megawatt from 50 kilowatts. The electrolyte what you use, that is phosphoric acid soaked in a matrix, and you can use it in distributed power generation application. The advantage is that you can get a higher gross efficiency with when you combine with CHP plants, cogeneration plants. Next, please. So then other three types are there. MCFC, their operating temperature is 600 to 700 degrees Celsius. The electrolyte what you use, that is solution of lithium sodium or potassium carbonates soaked in a matrix. You can generate a power output up to 3 megawatts from the lowest power of 300 kilowatts. Efficiency you can have up to 47%, and when you combine with the CHP plants, you can get 80%. You can use it in electricity utilities, and you can use it in distributed power generation application as well. And the merit is that you can have higher conversion efficiency, and you can also have a fuel flexibility. You can use any kind of fuel, provided of course you may have to use a reformer, and you can use variety of catalyst it can be suitable for cogeneration application. Then SYFC, the operating temperature is 600 to 600 to 1000 degrees Celsius, and the electrolyte what you use, that is 3R stabilized zirconia YSZ material, and it can produce power up to 3 megawatts. The conversion efficiency ranges between 35 to 43, and when you combine it with the CHP, then you can get 90%. You can use it as an auxiliary power, or you can use it as an electric utility device. You can use it in distributed power generation also. The maximum efficiency what you get, as I told here, that's 43%, and when you combine with the cogeneration, you can get 90%. So it offers very high efficiency, offers a high fuel flexibility, and you can use variety of catalysts, and you can use it in cogeneration plants. And of course, you can since the solid electrolyte, if it is used, it reduces corrosion and reduces electrolyte management problem. Then DMFC, of course, the operating temperature is up to 130 in the range of 130 to 200 degrees Celsius. Again, of course, here we use a proton exchange membrane. Then we have a stack power output up to 1 kilowatt. The efficiency is up to 30%, and you can use it in auxiliary power applications. Next, please. So here, of course, as I told, in automotive vehicle applications, generally we use proton exchange membrane fuel cell. That's PMFC. So here, of course, we focus how we can extract the heat in water, what is available in the product, and utilize further. This slide, it shows the proton exchange membrane fuel cell components, and how we can get energy out of that. So here at the top, you can see hydrogen fuel is channeled through field flow plates to the anode on one side of the fuel cell. So here you have plates actually. One side you have anode, other side you have plate. At the bottom you can see. At the bottom you can see anode and cathode. They are indicated, and between them you can see a pink color, that is called polymer electrolyte membrane. And of course, here we have one or two more components like bipolar plate, then catalyst, everything. Now, if you connect this anode and cathode, you get electrical power output. At the same time, you can see water is coming out from the fuel cell. So this water, when it comes out of the fuel cell as a result of electrochemical reaction, it will carry some heat. So that can be extracted. Next, please. Here, of course, this is one example what we have, PM polymer electrolyte membrane fuel cell, PMFC. So this, of course, this photo, it shows the fuel cell and how you get electrical power output. It was, of course, it was provided by a fuel cell manufacturing company called KPAS Electronics in Chennai. They provided this photograph. Next, please. So here you can see it's a test station. What you have? So fuel is supplied separately, air is supplied. At the bottom, you can see the front side. You can see black color tubes. So we supply fuel and air, and you get electrical power output. The left hand side, you can see a blue color box, that is load, connected load. Next, please. Now, this is of course fuel cell what you have, PMFC fuel cell, that is incorporated in that photograph, in the previous photograph. So the center part, that's very, very important. That is costly. Next. Next, please. So how, of course, we can use this fuel cell in automotive vehicles vehicles. This is an example. Of course, as I told in the yesterday's class, we can combine fuel cell with internal combustion engine, or we can combine fuel cell with electrical vehicle. Now, of course, there has been already hybrid vehicles. There have been already hybrid vehicles come out from in USA, Germany, UK, and of course Japan, everything everywhere. So here you can see Toyota. Toyota also it offers different hybrid vehicles. One such example is given here. IC hybrid vehicle, Prius. So engine is connected. Then you have primary battery and secondary battery, right? And the engine, IC engine, that is directly connected to wheels, that will drive the wheels. Whenever you want to operate with IC engine, that will produce power by consuming either hydrogen or any hydrocarbon fuel. You can have either petrol engine or diesel engine, whatever it may be, that consumes fuel. On the other hand, when I connect a fuel cell, right hand side, you can see this right hand side fuel cell that will produce electricity. That will, of course, that will be connected to electrical motor, that will be coupled to a electrical motor. That electrical motor will run the wheels. Next. So here, of course, the main focus of this topic is how we can utilize waste heat available from the fuel cell exit. So here you can see the top figure. It illustrates how the energy is obtained from a fuel cell, and what are the how it is obtained. So as I told, you can use a fuel cell with reformer or without reformer. As I told, fuel is supplied to a fuel cell, oxygen is supplied to a fuel cell. You get primarily you will get primarily electrical energy that is obtained from a fuel cell. In addition to that, you will have water and heat, and in some cases you will get tail gas. Now, the heat available in the form of in water, that can be utilized for getting secondary usefulness. So that way I'm going to talk hereafter in this presentation. So whatever you get a heat, that may be with a low grade or low temperature or high temperature, depending on the fuel cell what you use. As I told, we have PMFC, that is a low temperature fuel cell. High temperature fuel cell is SOFC. So when you use different fuel cells, you will get different temperatures available at the exit in water. So that can be suitably converted into different forms of usefulness. It may be mechanical power, it may be electrical power, or you can use it for cooling, producing cooling effect, or you can use it for miscellaneous applications, like you can get hot water, you can get you can use it for space heating, like this. So this I'm going to talk in the next few slides. Next, please. So how we can harness energy from this waste heat? As I told, you can get different usefulness. One is mechanical power, second is electrical power, third is cooling, and the fourth one is miscellaneous. For that, you need to have additional equipment. Suppose I want to produce mechanical power, I can use Stirling engine, or conventional SI engine or CA engine, Brayton cycle, which gas turbine, which basically operates on Brayton cycle, or Bryson cycle, or ORC, organic Rankine cycle, and last one is Kalina cycle. Then electrical power can be produced using thermoelectric generator, thermionic generator, and a thermoacoustic generator. Cooling effect can be achieved by using vapor absorption cycle or vapor absorption machine. Then miscellaneous, as I told, you can use the heat for water heating, further water heating, or preheating of air, or preheating of fuel, or you can use that heat for desalination application also. Next, please. So, if you see this Stirling cycle in internal combustion engines, thermodynamic cycles, as standard cycles, you would have studied Stirling engine or Stirling cycle. That Stirling cycle can be, Stirling engine can be coupled with a fuel cell exit, so that whatever you get the waste heat, that can be used to operate a Stirling engine. You can use air or helium in a Stirling engine, and you can get a secondary power output from the Stirling engine. Next, please. So how you can connect? Of course, whatever from the fuel cell. For example, if you take MCFC, from MCFC you get water, and of course that will carry heat. The heat available at the exit of the fuel cell, that will be given to operate Stirling heat engine. Next, please. So these are the examples of Stirling engines what we use. Different Stirling engines are there, alpha, beta, gamma Stirling engines. Now reciprocating engines, like as I told, you can use a petrol engine, you can use a diesel engine that you have studied earlier in your air standard cycles. Now, whatever the heat available in the exit of the fuel cell, that can be utilized either to preheat air that is supplied to the engine that is supplied to the engine in the case of C engine, or you can preheat the air and mix with gasoline in gasoline to form air fuel mixture in a carburetor, in a conventional carburetor engine. Then you can supply into the engine, or you can preheat fuel also. Why you need to preheat either air or fuel? Because at low temperature climatic conditions, the air or fuel has to be warmed up. Then only you will get, of course, the starting of engine will happen. So you have to raise the temperature of either fuel or air. So in that case, of course, if the heat available in the fuel cell exit, that can be utilized. Next, please. So then, of course, we have gas turbines which operate on, of course, Brayton cycle. Very large gas turbines, of course, can be combined with the fuel cell, especially if you operate with if you operate with the SOFC, which has a high operating temperature. Then in the case you can easily combine a gas turbine. But nowadays people are working on to reduce the gas turbine and produce micro gas turbine. Micro gas turbine can develop a low power output by availing the heat. So in that case, a lot of research works are going on. You can see the architecture of a micro gas turbine. As like gas turbine, here also you'll have compressor, and of course you have a turbine or expander, and of course combustion chamber is there. So this kind of small micro gas turbines, Japan and Germany, they're doing a lot of work in micro gas turbines. Of course, this micro gas turbine can be combined with the exit of the fuel cell. So whatever you get the waste heat, that can be, of course, utilized to either preheat air which enters into the compressor, or of course you can heat up. You can just heat up fuel here also, and then you can use it. Next, please. Of course, this is one example. Such example, you can combine SOFC, solid oxide fuel cell, with auto engine. So here, of course, you get one primary power output from the fuel cell and a secondary power output from running the auto heat engine. That means petrol engine. Can say next, please. Then, of course, how we can combine either auto engine or Stirling engine, whatever it may be. I'm just giving an illustration. For example, SOFC, it has a high operating temperature that you can combine with auto engine, or you can combine with Stirling engine. So depending on the requirement, you can use or you can combine this internal combustion engine. It may be auto or Stirling, or some people they use C engine as well. Next. So here, this is one illustration, molten carbonate fuel cell that is combined with a gas turbine, which operates on a Brayton cycle. So here you can see they use 4 different heat exchangers to extract the heat. So the energy from the fuel cell that is be given to heat exchanger, that is you can see to preheat air, to preheat the fuel in the compressor and turbine. In the compressor, you can preheat air and you can preheat the fuel, and of course you can just send the gases to the turbine for expansion. Next, please. So you can preheat continuously and then you can increase the power output of the turbine. Now here, of course, this is another way of combining the fuel cell with the gas turbine. Here, of course, they use pre-cooler and a recuperator arrangements. They are combined with the compressor and they produce heat. They produce power. Next, please. Then, of course, you can also produce electricity from the gas turbine. Then you can of course you can operate further small expanders. Now here one example is that PMFC, proton exchange membrane fuel cell, coupled with the refrigeration cycle. Although here I am showing like a vapor compression refrigeration cycle, but here the heat is given to evaporator, and of course the cooling effect is obtained. Actually, organic Rankine cycle, they also operate like steam power plant, what we call a Rankine cycle. Here we have such arrangement. PMFC, the heat which is obtained from the PMFC, that is given to an evaporator. Same kind of illustration we can use it here also for organic Rankine cycle. Now heat is given to an evaporator. Low boiling point refrigerant is used in the evaporator, that becomes vapor by absorbing the heat from the PMFC exit, and that vapor refrigerant is given to an expander. There you get a power output that is shown, power arrow mark at the top you can see. And of course, after expansion, the low temperature, low pressure vapor refrigerant that is given to a condenser. There it is condensed. Then it will be sent back to the evaporator. It may look like a vapor compression refrigeration cycle, but organic Rankine cycle we can use it similar way. That's why I'm just illustrating. I'm showing an illustration like this. So different reference are used. They have been investigated. They have been investigated for producing secondary power output in ORC, organic Rankine cycle, by extracting heat from different fuel cells. Next, please. So here, of course, here you can have gas turbine that can be combined with with the fuel cell in a different cogeneration cycle, like a topping cycle and bottoming cycle. The top one you can see, here you can see SOFC is used. The exit of the SOFC, that is, that is carrying heat. That heat is given to afterburner where air is supplied and heat is given there, and then then it is given to a gas turbine, right? So you get a power output from there, and we also get a recuperator which is connected at the bottom line. So you will get one more power from there. One is from the fuel cell and the other one is from the gas turbine. So these two will be connected to the grid. Bottom you can see bottoming cycle where you can see SOFC, it produces electricity, that is separate, and we connect the afterburner and then a heat exchanger. Air is supplied, fuel is supplied, and air fuel is burnt in a gas turbine. Then you get electricity. So we can use in the form of topping cycle or bottoming cycle to combine the fuel cell and the gas turbine to get two power outputs in the arrangement. Next, please. Then organic cycle, I told, of course, this left-hand side drawing I showed in the previous slide. So what is organic Rankine cycle? Normally, the Rankine cycle or modified Rankine cycle is used in steam power plant where you will use water as your working substance. But for low temperature applications, if you want to produce power output, then water cannot be used, but we can use low boiling point fluids. Normally reference, they are used as low boiling point working substance or fluids. Therefore, different reference, they can be used in organic Rankine cycle. So that arrangement I told in the previous slide. What we do, you allow the referent into an evaporator where heat is added, or the referent, low temperature referent will become vapor referent. Vapor referent will be given to a expander where it will produce power. After expansion of this after expansion of the referent, vapor referent, that will be cooled in a condenser. Then that will be again circulated back to the evaporator. So here you can see this illustration. The exhaust steam or exhaust gas which is coming out of the fuel cell, that is coupled or combined with an evaporator. So heat is transferred there to a referent. Then the organic Rankine cycle works. Next, please. So here you can see how we can combine PMFC with organic Rankine cycle. So at the center you can see a PMFC cell. Hydrogen is supplied through humidifier. Air is supplied to a compressor. Then compressed air is supplied to the cathode. Then you will get the power in the fuel cell stack. Then what happens? The heat from the fuel cell that is taken and there that is given to a low temperature referent. That is not shown here in the circuit, but of course low temperature referent that will get heat from the cycle, from the fuel cell exit, becomes vapor, and then vapor referent will be allowed to expand in a turbine, and you get a power output. Either you can get a mechanical power output. Suppose you get only turbine, then you can get mechanical power output. Or if you combine with the electrical generator, then you will get electrical energy, secondary electrical power output. After expansion, the vapor referent will enter into condenser. There it's condensed. Then it will go back to the fuel cell cycle. There, fuel cell arrangement. Next, please. Next, of course, this is Recuperative organic Rankine cycle is shown here. The fuel cell PMFC that is combined with recuperative organic Rankine cycle. That illustration is given. Only the modification what here is that and a recuperator is added in the cycle. Next. So as of now, people different reference were investigated and used in Rankine cycle, organic Rankine cycle, and the performance of the combined system, performance of fuel cell as well as the organic Rankine cycle were investigated. So here this table shows the properties of different different low boiling points used in ORC application is shown. Left side you can see, as I told, normally reference have low boiling point. Therefore, here many references are shown like R152A, R290, R123, R600, R600A, R601, R601A, R1234, Y1, YF, R1234 ZE, R1234 ZE, ammonia, propane, ethane, CO2, like this. Now their critical pressure, critical temperature, boiling point, triple point, all are given. Their ozone depletion potential and global warming potential are also shown in the last column. This you can go through. If you just see the boiling point, you can see the lowest boiling point. What you can see, that is -88, which is for ethane, and the highest boiling point is also there, that you can see. So whichever whichever referent you want to select, you can select and apply for your application. Suppose you want to do a project in MTech, then you can choose any one of this referent and you can calculate the performance parameters in ORC with and without combining the fuel cell. Next, please. So we can use different expanders for organic Rankine cycle. Actually, in expander, what we do, we allow the referent to expand so that you get a power output. So this I skip actually because of time. Next, please. Next, this also you can expand. Sorry, you can skip. So here you can see different expanders are shown in this picture. It may be reciprocating piston type expander, or a rotary type expander, or radial type expander, axial type expander. As you know, turbine, it can be given like this. So we can have any one of this expander or turbines to get the power output from the ORC. So according to the requirement, I can choose a particular expander, I can use it. Next, please. So this generally you can skip. Different turbines are shown, which are expanders that can be, that can be used in ORC, organic Rankine cycle. Next, please. This is a scroll expander. Next. Screw. You can skip. Rotary vane expander like this. Actually, Italy is prominent in producing this organic Rankine cycle units. Siemens company is one of the pioneers in manufacturing this organic Rankine cycle units that can be combined with waste heat recovery units. That can be combined with the systems which produce waste heat or generate waste heat. So this kind of organic Rankine cycle unit can be combined with a fuel cell, even in automotive application. Then thermoelectric generator, as you know, normally the thermoelectric generators, they use the properties of some materials that can use the effect of temperature difference. So you would have studied Seebeck effect, Peltier effect, Joule-Thomson effect. So by using different, different materials, dissimilar materials, we can get electrical power output or cooling effect when you combine or when you place between hot surface and cold surface. So you can use any one of the effect, either Peltier effect or Seebeck effect or Joule-Thomson effect to get either electrical power output or cooling effect. By the way, these thermoelectric devices are given in two forms. One is thermoelectric generator, and which produces electricity, and second one is thermoelectric cooler. So if you want to produce cooling effect by placing the different materials between hot and cold surface, then it will be called thermoelectric cooler. And if you want to produce electricity, then that device is called thermoelectric TEG, thermoelectric generator. Next, please. So the difference in that when you place the different dissimilar materials between two different temperatures, then you will get the heating or cooling effect. So the efficiency, thermoelectric generator efficiency, that depends on what kind of material we use, the efficiency of heat exchange between the hot gases and the hot part of the generator, and the the temperatures. So thermoelectric generators, normally TEG, they have different advantages. Mainly two advantages are there. There is no noise pollution. There is no vibration from the device, thermoelectric generator device. There is no moving part at all. Therefore, it will create very, very less friction in the entire system. We don't use any motor or pump like that. So in that case, absolutely, it's noise-free system. Disadvantages are three. Main disadvantages are three. One is low efficiency, conversion efficiency. Then the second one is high cost, and the third one is heavy weight of the system. So here you would have studied PN materials. So by placing these PN materials between hot surface and cold between two temperatures, you can produce electricity. So here one illustration is shown. A TEG is connected with the phosphoric acid fuel cell. So fuel cell, it produces electricity, and then the fuel cell exit, they are combined. The fuel cell exit that is located such a way that PNP materials are placed and they produce electricity. They are connected to a load. Here you can see at the bottom of the fuel cell, below the fuel cell, you can see PN materials are placed and they are connected to a load. Okay, next. Some people, they used, of course, direct carbon fuel cell. They are combined with thermoelectric generator. So here we use a regenerator as well. Next. Some people have tried with solid oxide fuel cell, SOFC, and they combine thermoelectric generator with the solid oxide fuel cell. So from SOFC will get a primary electrical power output, and by keeping this PNP pairs, you will get secondary electrical power output. Next. And of course, we have one more device called a thermionic converter that consists of a hotter emitter electrode from which electrons are vaporized by thermionic emission, and a colder collector electrode into which they are condensed after conduction through the inter-electrode plasma. By doing this, we can get some electrical power from this system. So normally we get in the form of current, typically several amperes per square centimeter of emitter surface. So you'll get power, power up to what you call 100 watts, like that. Depending on the efficiency, we'll get conversion efficiency, will get 10 to 100 kilowatts. So the temperature, emitter temperature, that will be in the range of 1500 to 2000 Kelvin. Okay. And cesium vapor, that is normally used to optimize the electrode work functions. And you will get the maximum efficiency when you use such kind of material. Next. So here I'm just showing an illustration how a thermionic converter is coupled with the fuel cell. We have anode, cathode, in between that electrolyte is there. Then a reformer is there. That reformer, of course, it reforms the fuel which is fed into the anode. And cathode side, the thermionic converter is combined. Next, please. Previous one. So thermionic converter, of course, that is shown here in this slide. Next, please. So some people they have adopted. Some people they combined this thermionic converter with SOFC also. Here you can see this arrangement. Next. Next, please. Yeah. Some few research works are there on combining thermoacoustic system with the fuel cell. What is the thermoacoustic effect? It is the interaction between the temperature, density, and pressure difference of sound waves. When sound waves are created, you will get some positive effect that can be harnessed. So that's called the thermoacoustic effect. This thermoacoustic effect can be used to produce mechanical power. So thermoacoustic engines, they are devices that use high amplitude sound waves to transfer heat from one place to another place, or vice versa. So by the way, this thermoacoustic system can be combined with a fuel cell. So different types of thermoacoustic systems are there. One is constant wave thermoacoustic system, and the second one is variable wave thermoacoustic system. So with the help of the heat available in the fuel cell exit, you can just get the acoustic effect, and then it can produce power. Next, please. What are the merits as like TEG, thermoelectric conversion, thermoelectric generator? Here also there is no moving part, so it's noise free system. You can use it for low temperature to medium temperature, and here, because there is no friction, you will get high reliability. But what are the disadvantages? Low, it can produce only low power, but you need a big size of the equipment or system, and it has to necessarily use fluids with a high viscosity, and it will give low efficiency because low power is there, low power output is there, and because of that you will get low efficiency. And there is a complex construction and high cost of production involved. So as of now, it is in research level only to combine with fuel cells. Next. So here, of course, molten carbonate fuel cells, when you combine with the different waste recovery systems, like combining with Stirling cycle, combining with gas turbine, combined with thermoelectric conversion, like that, how you can get efficiency with varying temperature, operating temperature. That is illustrated in this picture. So different arrangements are given, like TPVC, that means a thermophotovoltaic conversion, that I didn't tell here. Then thermoelectric conversion, thermo thermionic converter, Brayton cycle, gas turbine, Stirling cycle, all results are included in this picture. You can see. So the maximum conversion efficiency of up to 55% you can obtain by combining these systems with a high operating temperature of 925 Kelvin. I'm sorry. Next. So other applications like miscellaneous, in which you can heat up water, you can preheat air, you can preheat fuel by availing the heat in the fuel cell exit. So this illustration shows how we can preheat hydrogen, which is supplied to the fuel cell itself as a fuel. So here fuel cell stack is shown at the center. Waste heat is coming out from the fuel cell stack, that is given to a heat exchanger, and at the bottom you can see left hand side bottom you can see H2 reservoir. That means hydrogen reservoir where hydrogen is stored. From there hydrogen is supplied, that goes to heat exchanger. There it is preheated by availing heat from the waste heat steam in a heat exchanger. Then preheated hydrogen is supplied to the fuel cell. So this way, of course, you can heat up or warm up the fuel which enters into the fuel cell stack. By doing so, we can increase the electrical power output and conversion efficiency as well. Next, please. So here, of course, this shows, of course, a biogas which can be used as a fuel in a fuel cell. That is shown here. Here at the top, you can see an anaerobic digester is there, from which you get biogas. That biogas is given to pre-treatment equipment. Normally, you have to remove carbon dioxide, sulfur, hydrogen sulfide, which is present in biogas. That has to be removed. Then that is given to a reformer. Biogas is given to a reformer. Then, of course, that reformed gas that is given to a fuel cell. So here at the bottom you can see fuel cell power system, where you will get the reformed gas. Normally after removal of the carbon dioxide, hydrogen sulfide from biogas, that will be given for reformation, and then you will get hydrogen that's supplied, and oxygen is also supplied to a fuel cell. Then you get power output. Now, left hand side you can see whatever you get the heat, that is stored in a thermal storage device. Whatever you get the heat in the fuel cell exit, that can be stored in a thermal storage unit, that is shown at the bottom left hand side. So after storing the heat, whenever you want, you can avail it in the form of hot water. So that is shown at the bottom, right? So one side you are producing electrical energy from a fuel cell. Other side, whatever you get the heat, that is first stored in a thermal storage tank, and then you can avail for producing hot water. Next, please. So here, one cogeneration plant, combined heat and power system with the PMFC, that is shown here. So here, of course, as I told, whatever you get waste heat, that can be stored in a storage tank, thermal energy storage tank, and then you can use it for later purpose. So by this way, you can see at the top, you can see a fuel processor unit in which fuel is supplied, air is supplied, and then the fuel and air that is supplied to fuel cell, which is shown at the center of the slide, right? And whatever you get electrical power output, that is given to a load. And bottom right, you can see a heat exchanger. In the heat exchanger, what you do, the temperature, the waste heat steam from the fuel cell that is given to a heat exchanger, and that heat is transferred by another substance, and that is given to a hot water storage tank. So that is normally you call it as thermal energy storage tank or hot water storage tank. Whichever form you want, you can store. Either you can store in the form of water, or you can store in different mediums. Then here it is showing hot water storage tank. From hot water storage tank, you can take water and then you can use it for further application. Next, please. That one. This, of course, heat pump also you can use. You can combine with a fuel cell, that you can skip. Next, please. So here, of course, the outcome of different research so far, what they have done to harness waste heat for usefulness is shown here. Left hand side, first column, it shows the type of fuel cell what they use. Specific research ideas are given at the second column. Third column, analysis type is given, and the last one, conclusion are given. So either you can do numerical, and they have done a numerical analysis or simulation, or of course experimental. They have done, their summaries are given here, that you can go through that. Next, please. So this one, of course, you can also use the waste heat to operate a vapor absorption chiller. You would have studied this vapor absorption refrigeration system, which uses either low grade heat or waste heat to operate the refrigeration system. So what is the advantage of vapor absorption refrigeration system is that there is no compressor. So only by availing heat, you can increase the pressure of the refrigerant, and then you can get the cooling effect. That's called the vapor absorption refrigeration system. So here the fuel cell exit, it carries some heat. That heat can be utilized to raise the pressure, temperature and pressure of the refrigerant in the vapor absorption refrigeration system. Normally we call it as absorption chiller. So by combining the vapor absorption system with the fuel cell exit, you can get a cooling effect. So one way you get electrical power output from the fuel cell, and the other side you will get cooling effect from the vapor absorption refrigeration system, or vapor absorption chiller. So here you can see that illustration how they are connected. Next, please. So here some people, they have worked with the fuel cell and vapor absorption systems. Their specific research idea, what kind of analysis type they did, and conclusions are given when they combine absorption chiller with fuel cell. That you can go through that. Next slide, please. Next slide. Here you can see for desalination application also we can use fuels. We can use this waste heat that is obtained from a fuel cell stack. So here you can see this illustration. Fuel cell stack is there. You get electrical power output. At the same time, waste heat which is coming out of the fuel cell, that is given to your desalination unit. Normally, desalination unit, what it does, it removes the salinity of water, so that you will get potable water. So here, seawater is allowed into a desalination system. The waste heat is utilized to what do you call, evaporate the seawater, and you get the fresh water at the bottom. Next. No, previous slide, please. So here, of course, we can also use reverse. You can also use the waste heat obtained from the fuel cell stack to operate reverse osmosis process. That idea is given in this slide. By combining reverse osmosis plant, you can get fresh water. Okay. Next. So here we have seen different energy conversion systems or other devices to utilize waste heat available in fuel cell. So different methods I told. The summary of the all these works are given here. The gas turbine can increase the overall electrical efficiency of the fuel cell stack if the stack operating temperature is substantially high. That means it should be greater than 250 degrees Celsius. Then we can use gas turbine. Uh, by that way, of course, large scale temperature fuel cells are generally more suited for integration with the gas turbines, such as solid oxide fuel cell and all. Thermoelectric generation or thermoelectric generators can also increase the overall electrical efficiency uh, because it has a very simple, relatively simple structure, and you can use it for small application. But the problem is the conversion efficiency is very, very low compared to other devices. You can integrate absorption chiller with the fuel cell. That is a better choice for wherever you need cooling effect or cooling demand. And desalination plants, they require both power and high grade heat to achieve high efficiency operation. Therefore, we can integrate the fuel cell, especially solid oxide fuel cell, which is having a very high operating temperature, that you can combine with the desalination system so that you can get better power, better water output. Next, please. So whatever I told the summary, that's very important summary points. Others also you can get it. So with this, I end up my lecture, end up my presentation. Thank you for listening. If you have any queries, you can ask.
If there is any query from the participants, one or two questions if you want to ask to sir. So if there is no query, I like to thank my sincere gratitude to Professor S. Murugan for delivering his lecture on waste heat recovery options from fuel cells, which is a current cutting edge research field in the field of energy applications and efficiency. Thank you very much, sir, for your time.
Thank you. Thank you very much.